Okay, hello everyone. We are going to get started, so please find a seat. I think there's still some room available. Thank you very much for coming. For those of you who are new, these are the ICARL seminars that we run monthly. Although next month we will have some extra surprises we will tell you about at the end of the talk. So today we are very honored to have with us Felix Hill. He's a research scientist at DeepMind, where he works in the intersection or in the way through language to general intelligence. And I have to say that for those of us who have been working on grounded language learning, compositional generalization, and also object-based learning, we have been really impacted by his work. We're very happy to have him here today. So without any further delay, stage is yours.
Cool. Thanks, Borja, for inviting me. It's really great to have so many people here to share some of our work that we've been doing on these topics in DeepMind. Cool. So just to get everyone kind of warmed up, I'll start with a little fun example, right? So I've been interested in language understanding and how humans understand language for a long time. But of course, an interesting thing about language is there are sentences which seem a bit grammatical, say, or they seem like they kind of have approximately a sensible structure, but when you read them, they're just completely nonsense, right? They don't actually make any sense, right? So here's an example. The haystack was important because the cloth ripped. So something feels right about that, but when you ask people, you know, does this make any sense to you? They're like, oh no, that's crazy. That's absolute nonsense. Maybe the person who wrote this had some sort of semantic dementia or some other sort of aphasia. There's no way that anyone who was, you know, kind of in their right mind would ever say anything like that. But of course, what's actually really interesting is that if you then put them in a particular context in the world, say, for example, show them a video like this, and then you encourage them to read the same sentence, think about exactly the same sentence. Something goes on, it seems like a bit of cognitive load is exerted, and finally they say, actually, no, that sentence isn't complete nonsense. That could plausibly make some sense. In this context, it is possible to derive a coherent meaning from that sentence and use it to maybe decide to do something better in the world as a consequence of having received that information. So the point of this example is just to highlight the motivation behind a kind of working hypothesis, which underlines a lot of the work that we've been doing in our group in DeepMind. We're interested in building a perfect, or certainly a very improved language understanding system. But of course, DeepMind as a whole, and that includes us, are interested in building a generally intelligent agent as a kind of more general goal. And so the work of our team is kind of aiming to explore the extent to which these two things are interrelated, right? And one working hypothesis is the one I've written here, which is that in order to build a perfect language understanding machine, we may actually, in order to get absolute perfection in language understanding, we may actually need something which is almost as generally intelligent as a smart human is. So it might need to be good at all the other things that humans are good at, like exploring an environment and making sense of the world through their eyes and other senses, and being able to control things using their limbs and all of those other challenges. So that's our working hypothesis. But of course, not everyone shares it. And indeed, not everyone in DeepMind shares it. So there are a lot of people who've had an enormous amount of success by kind of either sort of proactively not paying any attention to natural language, or maybe just kind of not necessarily realizing that it's an interesting facet of intelligence. And of course, a lot of these projects I'm going to talk about, well, I'm not talking about them, but I'll show you these examples of great successes through just kind of reinforcement learning on its own. Certainly, it's true to say that there was no analog to the sort of natural language that humans use to communicate in the systems that had great success, for example, at beating the world's best person at AlphaGo, or at beating the world's best player at StarCraft, or folding proteins, or these other great successes. So these results have led a lot of people to think that maybe just a pure reinforcement learning approach is in fact sufficient for getting to a generally intelligent machine. But I guess we're kind of betting on a slightly different approach, which is the idea that certainly if we think about how humans learn, language seems to play an incredibly important part in the development of humans, at least within one generation. And so maybe by analogy, it could be critical to building the most flexible and general machine learning systems. So I'm going to show you 4 results at a very high level from our group, which I think give at least circumstantial evidence of the role of language in getting machines to be able to do things which, at first blush at least, don't actually have anything necessarily to do with language. So clearly, if you want to train a really good system which takes language in and gives language out, that system ought to be exposed to some language at some point. But hopefully these examples focus on things which aren't necessarily intrinsically about language. And the results kind of show that even in those cases, language can help these machines to become smarter. So in the first case, I'm going to focus on this topic of embodiment, the idea of what it means to be a learner that actually exists in some point in space, kind of takes in the world from a first person perspective, and what the effect of having that stream of experience actually has on biasing the way that the learner comes to be. So the setting I'm going to use for almost all of the reinforcement learning experiments I talk about in this talk is the following. So this is a slightly messy schematic, but it's kind of simple conceptually. So you can imagine that this is the graph of the agent. The environment might exist here, and the agent experiences the environment in 2 ways. So it either hears or receives some language, in this case is actually going to be in the form of a string, or it sees the world, and that's in the form of raw pixels. So it sees almost like an image taken through the eyes of wherever the agent is at that moment in time. And it's obviously influenced also by the direction that the agent's head is turning and things like that. So those 2 observations, the agent receives them at every step in time in the environment, and it might combine those information. So in this like sort of default architecture, it might process the vision with a convolutional neural network. It can embed the language into some vector. We used an LSTM in a lot of experiments, but this could easily be a transformer or even just an additive embedding model. And then those are combined in some way at every time step. And then importantly, the agent itself has some sort of memory. It has a facility to integrate knowledge across time steps, to kind of combine not just immediate past experiences, but more distant past experiences in order to determine the decisions it takes. And conditioned on the state of that memory, we produce a policy which is basically just a distribution over the possible actions that the agent can take. And in the environments I'm going to talk about, there's different numbers of actions, some mix of discrete and continuous, but you can think of it as a space of like 128 different possible predictions at every time step, something like that. Cool, okay, so the first bit that I'm going to talk about refers to this idea of studying the generalization capabilities of agents once we've used that architecture and trained it in different ways. Okay, and in all of these experiments, I'm just going to use a very vanilla reinforcement learning, policy gradient reinforcement learning loss. So the details of the learning algorithm are not too important. And I can point you to papers where we go into that, but I just want to instead spend a bit of time explaining the structure of the experiment. So this is a test of whether we can get an agent to generalize in a compositional way. And you'll recall that the structure of the agent is kind of neutral in the sense that there's nothing specifically in it apart from generic neural network components, right? So the architecture of the agent isn't set up to kind of promote one particular type of extrapolation or generalization beyond the training experience. It's kind of neutral with respect to that. And we're going to train the agent to teach it various things. So the first thing we want to teach it is the name of all the possible objects that appear in the environment. And how are we going to know if the agent's learned the name of all the objects in the environment? Well, each episode, there's a few different objects randomly scattered on the floor, and we're going to train the agent. We're going to give the agent an instruction. It's then going to go and pick up one of the objects. The instruction always refers to one of the objects in the environment. And if the agent moves around the environment, finds the correct object and lifts it up, then we'll give the agent a positive reward. And if it lifts up an object which is not the right object, then the episode ends and it doesn't get any reward. So in order to get a reward, it needs to know kind of at some point in its weights, it needs to come to understand what each of these word strings mean and how they refer to the objects in the world. So we'll train the agent on episodes where any possible of the objects in the world provide the instruction. So if the agent gets maximum score on those sorts of episodes, we know that in some sense it knows the words for all of the objects in the world. But we're also going to train it to do something with more sort of active with those objects. So we're going to actually train it to lift up the object and put it on the bed. There's a big bed in the room. It's actually like, we chose a bed because we didn't want to fixate on the problem of learning a really difficult motor control action. So the bed is kind of the easiest thing to learn because it's low and flat. And so the chance of finding how to do that through just a crude reinforcement learning is a little bit higher. But importantly, in the training episodes, we're only going to train and reward the agent for lifting up a particular subset of all the objects that it's been lifting, right? So it's only the agent in its training experience has only ever lifted up some of these objects and put them on the bed. But it does know what each of the objects mean because it's been trained to lift them, right? So it knows all the words, but it doesn't know, it's only had practice of doing something with some of these words or some of these objects. And then we're going to have certain held out episodes. There's no reward in these episodes. So the agent doesn't learn anything, but instead, they're just there to track the score. So they're just there as an evaluation to measure how well the agent kind of extrapolates its knowledge of what it means to put something to objects that it's never seen before. Okay, and then we're going to give experiments of exactly this type in 2 different environments, right? So the environments are intended to be analogous. They have the same number of total objects. In some sense, they have the same vocabulary, but in one case, it's a top-down grid world environment. And in the other case, it's a 3D first-person environment with a much finer grained action space. But at some high level of abstraction, both of these environments are exactly the same. So you can kind of see what the environments are like there. And what we found, which is intended to kind of make a point about the role of learning in embodied settings and learning from first person like animals do, is that the agent that was trained to do this in the more difficult, well, more, say, naturalistic 3D environment, actually is able to extrapolate this knowledge and generalize in a systematic way, much better than the agent that was trained in the grid world. So here you can see the 2 curves that go to the top of the 2 performance of the agent on the training set, where it was actually being rewarded. And then the blue line is the performance on those held out samples. And it gets about over sort of approximately 80% or up near 80% on the 3D environment, but much closer to 50% on the grid world. So we thought, well, this is pretty interesting. And we must have had, I guess we had some intuition that there might be an interesting difference here. In some sense, you can think of the 3D world as being richer. It provides the agent with many different frames to look at the objects. And we thought maybe that's part of what's making a difference here. But when we did a bit further explanation, we isolated the really important aspects as this notion of egocentricity, right? So if you are an agent in a particular place in the world, then certain things have certain states in the environment have an invariance to you, right? Like lots more things look the same in the world if I'm seeing everything from this point of view than if I'm seeing everything globally and top down. And that can lead to certain types of inductive biases in the learner, which encourage it to generalize in different ways. So by taking the 2D grid world and imposing sort of egocentricity on it, so now we're in an environment where the agent is always at the middle of the world. So this isn't like kind of first person, but it is egocentric. Whenever the agent, this grid, the agent's the white thing, whenever it takes an action, the world moves with it, the window moves with it. So it's kind of controlling its own world. And that introduces a certain invariance, right? Because you can see this thing could look to the agent the same as the equivalent thing at the top of the environment in a way that it wouldn't do if it was a global agent. And this explains almost all of the difference in generalization from first person perspective to third person perspective. So this is a small result, and we have lots more results of a similar fashion in the paper. This paper came out a couple of years ago now, but I think it's intended to point out one aspect in which language, which in this experiment comes in the form of the instructions that the agent get, and this notion of putting, right? We're in some sense, we're giving the agent a number of concepts. The one concept is certain noun concepts are the concepts of all of the objects in the world, but there's also at least one verb style concept, which is the process of lifting up something and putting it on the bed. And it's that thing which seems to be more amenable to learning from a first person perspective than it does from a third person perspective. It's that general concept which you can generalize better. And I think that tells us some story about how language evolved as a kind of like the word put and that whole notion is somehow inherently, it involves like taking something and having it near you and then putting it down somewhere. And potentially it's that interrelationship between how language is kind of built up and evolved as a system for first person agents to talk about each other. And it's that correspondence which is maybe behind some of the effect that we're trying to highlight here. But you know, it's a lot more remains to be understood about effects like this. Cool. Okay, so I'm going to go to a slightly different topic, which is like the idea of how we can understand better the structure and the relations in our environment. And again, I want to try and make the case that language can be really important in helping machine learners to get a handle on these things, even on non-linguistic tasks. So this is work led by Andrew, who's in our group. And it focuses on this notion of explanations. So when humans learn something, humans do regularly learn through something a bit like reinforcement learning, where they get a very scalar kind of approximate signal for whether or not something went well or not. But they often also, and in particular in places of formal education, like a university or a school, learn through a type of explanation, which is where people who already know how to do something kind of explain to them why something has gone well or why something has gone badly. And that information carries a lot more signal than just a scalar reward. And humans have got pretty good at taking that information and using it to need fewer attempts to do that thing than they would do if they were just trying and getting a scalar reward. So there's lots of work in psychology which shows how powerful the notion of explanation is for human learning. And of course, if it wasn't powerful, then this wouldn't be standard practice for teachers, right? They scribble all over your work. And the reason is because just by marking things correct or not, they wouldn't convey as much information as if they did this as well. So that's why I think they do it. So we're going to bring this into the setting of an embodied RL agent in the context of these odd one out relational reasoning tasks. So to kind of jump ahead, this is a cognitive task which requires relational understanding. Versions of this that we talk about in the paper also require a notion of actually experimenting causally on the environment and seeing what happens. But in all cases, when we give the agent something a bit like explanations as well as reinforcement learning signal to learn from, it masters these tasks much better than in the case where it's forced to learn just from reinforcement alone. So I don't know if you can work out which one of these four objects is the odd one out. So firstly, you might have an intuition. But you're going to get the full idea in a generalizable way very quickly if I just explain to you. So that in itself is intended to point out the value of explanation. So the rule is there's certain types of features that can vary. And one of them might be color, one of them might be size, one of them might be texture, and one of them could be shape. Now, all of those features, on each of those feature dimensions, there's at least two shapes here that have the same value, except for one, right? And that one is color. So in this case, it's the color that determines the odd one out, but that's not necessarily the case. It could be any of them. It's not texture that determines the odd one out because those two have the same texture. It's not shape because those two have the same shape. And it's not size because there's two small ones and two large ones, right? So it has to be color. And given that it's color, knowing that this green thing is the odd one out is then trivial. So that's the reasoning process that the agent has to go through. And it's, okay, yeah, so that's what an explanation might look like. And in fact, this is precisely what so in one situation, we gave the environment kind of like, the environment spits out this. So if the agent gets it right, it says, you picked up a pentagon, it's right because of these reasons. And in the other condition, it just gives you a positive or negative reward. So in both cases, it gives you a reward, but in some cases, there's this language in coming out into the environment as a sort of like simulation of a teacher. Okay, yeah, this is hard because if you actually look at any subset of these, the answer is ambiguous. You can't know the answer unless you look at all four objects. And in particular, that's challenging in this first person setting because it becomes like a reasoning and memory problem because the agent needs to kind of explore the world, see what the four objects are, retain in its activations like its memory of what those four objects were, and then do the reasoning in order to actually find the right one and pick it up. So it's a difficult task. And yeah, as I said, the explanations first tell you what you picked up. So that provides enough signal for the agent to kind of ground these weird string signals to the actual features of the objects. But at the same time, it also provides a string a bit like that, which actually explains why the trial was successful or not. And how do we use that extra information which comes into the environment? So in this experiment, there's no language going into the agent in the form of an instruction. All of the language the agent's learning from is actually this post hoc explanation which is spat out at the end of the episode. How does the agent learn from it? Well, in fact, we don't put that into the agent. If you put that in as an input to the agent, it could lead to a situation where the agent can only do, at test time, you need these explanations to do well, right? Because the agent will get used to that. Used to these explanations always being there. But we want an agent which learns the task. It's a non-linguistic task, right? It's an odd one out task. There's no language in the task per se. So we want an agent which learns to do this task and doesn't need the language there when it does it well, but it somehow takes advantage of the language, and the mechanism we use is this notion of predictive learning, right? So we just train an additional auxiliary head to predict the language that happens to be in the environment. And the loss from the predicting that language is just the maximum, the likelihood of those words is back propagated, like the agent's likelihood of those words is used to backpropagate a loss into the memory of the agent. And then, of course, the standard policy gradient loss is also backpropagated if the agent gets a reward. Okay. Cool. So what happens? Well, you know, as you can probably guess from the fact I'm talking about this, it makes a huge difference to what the agents can learn, right? So it's actually like substantially better at learning these complex reasoning tasks if you give it this language signal as well as the RL signal. Now, some people say, well, this is trivial. You kind of give it more information in one case and it learns better. That's true, but I think it's about the nature of the information that we give it. And I guess it's intended to show that at least, so I'm not saying a pure reinforcement learning agent cannot learn this task. It might do, and reinforcement learning algorithms will probably get better. So if it can't do now with the best algorithm in the world, it might do in the future. But the point is, at this point in time, RL does not solve this task, but RL combined with language as an explanation does solve this task. That in itself, I think, gives some indication of the value of using language if there's a nice, plausible way to use it. And that's certainly what humans do. Some people have done work sort of pointing out that convolutional networks like to sort of fixate on certain features that are maybe more superficial or obvious and not pay attention to the more difficult to isolate features in the world. And our network is trained end to end as the agent learns. So it's likely that the convolutional visual features that it extracts do focus on these easy to isolate features. And you can see here the explanation, when the odd one out is determined by texture, that's the case where the explanations make the most difference. When the odd one out is determined by position, that's super spatially sort of salient because there'll be just 3 objects on one side of the room and 1 on the other. You don't need explanations to learn that. So it seems to be that language is helping us to bring out kind of the most important, difficult to identify features in the environment. And I guess that's true when you think about how we learn in school. You know, the obvious stuff is not what the teacher said. They focus on the less obvious stuff. So we know that for convolutional networks, texture is harder, color is easier, and that's sort of it seems to be that in the harder cases, it's the time when explanation-based learning is actually making the most difference. Cool. Okay, so I'm going to move on to this topic of exploration. So one other known limitation of reinforcement learning is that you know, for very hard exploration problems, it seems somewhat futile. So like learning to explore while also learning to do something else seems like a really hard chicken and egg problem, because actually, if you think about how humans explore, they, you know, like it's almost like you need a conceptual understanding of the world before you can explore. But how do you learn about the world if you haven't got good ability to explore? And of course, we've solved this, like animals have solved this over millions of generations by trying a lot of stuff. And that typically doesn't scale very well if we want to kind of get intelligent machines in a lifetime. So we were interested in this notion of, well, what if we had a bit more prior knowledge? Could we perhaps use that prior knowledge to learn to explore better? And in particular, maybe some basic knowledge of language would help an agent to explore better on otherwise non-linguistic tasks. So this is work led by Alison Tam, who's there. And we focused on 2 3D environments, right? So one of them is this city environment, which is intentionally really big. So that, and we can just look at exploration metrics, right? So I'm not going to do any tasks per se here. I'm just going to measure how well agents randomly explore. Like how many different streets do they naturally go to if we leave them under different exploration conditions? And then this is a house where we can again measure. Well, here we actually do give it some tasks. So we give it like, I need you to find an X, but of course, finding an X could involve going into all of the rooms. So an agent which can explore well is naturally going to learn that task better. Okay, and then this work is not like totally focused on the problem of coming up with better sort of mathematically motivated exploration algorithms. It's more a study of the role of prior linguistic knowledge in enabling existing exploration algorithms. And in particular, we focus on a subset of exploration algorithms which can be considered novelty-based. So these are 2 well-known novelty-based exploration algorithms, but essentially they work in both the same way. So they work on different time scales, but the whole principle behind them, I mean, some of you might be experts in exploration. I'm not, but one thing I know is that these novelty-based algorithms approximately work in the following way. So the agent records in its memory some notion of all the things it's experienced in the past. And then whenever it experiences something new or some new state, it compares them. It makes a comparison between the current thing it's experiencing and all the things it's experienced in the past. And if that thing is under some metric, very different from the things it's experienced in the past, then it gives itself like a little intrinsic reward. But if it's very similar, it might match one of them identically, or at least it might be somehow in the middle of the average of all of its past experiences. It won't give itself much intrinsic reward. So by doing that, you get a situation where the agent is motivated to go to places that it's never been to before. So that's approximately how they work. But of course, this notion of what it means to go to a place you've never been before is quite subtle, because, like, for example, those two states are very, well, they're not very different, but those two states are different. Should you reward yourself for experiencing this state having previously been in this state? And I think we would say, well, it's not actually that cool if you reward yourself for that. And then imagine you come across a television which is just showing like random static patterns. Under the kind of naive application of one of these novelty-based algorithms, you would find that incredibly stimulating, right? Because it's always different from the thing you were looking at momentarily. And then you'd get trapped and stuck and you'd just be looking at this TV forever. And I don't know if anyone's got young children who they've sort of left in front of YouTube while the video's gone on to the next one, and then the random ones that they throw to children after that. But you'll notice that a lot of them do kind of have that property. And I think that tells us that young children actually do have this tendency to be incredibly stimulated by like just radical novelty. But for adults, certainly we'd get pretty bored of that television situation quickly. And the hypothesis is that that's because we've learned to abstract our world into a different state space in which novel things, like things that are really novel in some sense, do entertain us, but other things don't. And maybe that state, that ability to abstract the world is informed a bit by us having language. So the hypothesis here is that if we think of that thing not as a load of particular pixels, but instead a TV showing colorful patterns, then even if the screen changes, that thought doesn't change. And so I'm not stimulated by that. I don't find that novel or interesting. And the same for these three here. They're different states, but they're, to us, at least linguistically, they're all the same. And so I'm not going to reward myself for finding those novel. So we tested this in a kind of learning-based way by comparing two ways of representing the states of the environment. So remember, the agent receives everything from a first-person view, and it gets pixels. So one way is just by embedding them using a vision. So in none of these tasks is there any language, or at least in one of them there is an instruction, but I'm not focusing on the language in the environment here. I'm just focusing on the way that the agent embeds its visual experiences. In one case, we use just a classic ImageNet network. So this network is kind of like non-linguistic in the sense that the categories that it's learned to predict, given an image, are orthogonal and just random symbols. They represent a random set of words that don't have any, for the network at least, they don't have any connection to each other. And then in a different condition, we're going to consider a model which was trained to understand images, but to embed them in a joint space with words. And those words come from captions across the internet. So that's the clip style architecture. So the sort of implication is that this model, even if we only use the image encoder, is sort of infused with knowledge of how the abstractions fit together linguistically. And as a consequence, it provides a different abstraction of the state space in an agent. And as you might have guessed, because that's why I'm talking about it, we find that the model whose abstraction of its state space is informed by a clip or an align style model, so that's the green or the red here, if the agent explores based on novelty in that space, it ends up exploring its environment much more comprehensively than an agent which explores based on a purely image-based abstraction, which comes from an ImageNet network, or from some baseline network, which was kind of trained using an autoencoder on the environment state itself, right? So both of those conditions don't have any language in the mix. This is another small anecdotal piece of evidence that an ability to understand the world and make abstractions in terms of language can allow us to do more, give us a sense of novelty, which allows us to explore the world and find richer experiences. Okay, cool. I don't know what the intention of that slide is, but oh yeah, I do now because the video's come. So the intention of this slide is for me to show you from above what happens to the agents trained in the two conditions, right? So the one with the clip encoder ends up doing this, and the one with the ImageNet-based baseline does that, which, as you can see from this weird visualization, doesn't cover as much of the same city in the same amount of time. Cool. Okay, so that's a connection between language and exploration. And so I'll just check how I'm doing on time. And then finally, okay, so finally, I'm going to tell you about this interaction between language and memory and adaptability and few-shot learning, right? So I'm going to say that if we learn language, that will increase our ability to flexibly adapt to new situations. So that's the kind of high-level hypothesis. And this was work that was led by Stephanie. And I should warn you that this isn't actually about an RL agent. So I'm kind of stretching things a bit, but I'll loop it back to the RL setting at the end. Yeah, people adapt quickly to new situations. I think, well, by some definition of people and by some definition of quickly, that's probably true, as you can see from this. And so we're interested in getting neural networks to be able to do similar things, right? So when people always said, oh, neural networks, they're very slow learners, they need a lot of samples to pick anything up. And, you know, if you certainly study things like Bayesian inference, you'll realize that training a massive model on loads of data is a slow process, and it doesn't actually reflect a human ability to kind of pick stuff up quickly. So people initially thought, like going back to the 5, 6, 7 years, people thought, well, actually, I can think of, now that neural networks are getting better with their memory, I can think of ways to actually kind of get them to be more flexible in the way they acquire knowledge. And that was this process that we think of as meta-learning, right? So the way that this works is that I, as the experimenter, very explicitly get the network used to being flexible by making it be flexible as I train it. So it was always demonstrated in the context of image classification, but the idea was, imagine that I want to teach the network the name for a new category. So I'm going to show it an image of the network, and it has to immediately, just from that one category, say, okay, now I show it another one, and it says, yeah, I know what that is. That's a number 1. So if I want to get a network to do that, I'm going to give it a category and a number, a label, and a category and a label, and a category and a label. And then I'm going to ask it, okay, now you see this category, what's its label? And it's going to be one of the ones I previously showed it. But importantly, the trick is that I need to shuffle the right labels for each image as I'm training it in order to get it used to the fact that it can't rely on its previous knowledge. Like, I saw that like many, many samples ago, so I'm going to just tell you what that thing is. I need to look back at the immediate context to tell you what it is, because I can't rely on previous samples. Why can't I rely on previous samples? Well, because the labels are constantly changing every episode, so it's not going to give me the right answer if I do that, right? So that's how meta-learning works. So by basically shuffling up the world, you can get networks to be more flexible, which is a really cool insight, right? And it surprised a lot of people. And indeed, it led to a solution for this omniglot challenge, which Brendan proposed, which was kind of born out of an idea that, well, Bayesian networks and those sorts of mechanisms with much stronger inductive biases are able to learn categories from a small amount of experience. Maybe we need can a neural network ever do something like that? And meta-learning was the initial solution to that, right? So we could, by flexibly shuffling the world, we could get networks to be able to pick up the name for one of these categories and repeat it back in 1 or 2 experiences of that category. But then what happened more recently was that people noticed that this flexible ability to learn quickly was also inherent, implicit in language models. Right now, language models, and even neural language models, have existed, you know, for 30, 40 years. It's only recently that they've started being able to do things like this, right? So this is an example of a language model learning very, very quickly. It does a language model, and if you give the language model the word cheese, it might respond to that, and you know, if you're lucky, it will respond with a reasonable continuation. So it might tell you what cheese is. It might say cheese is a food made from milk, because that's a very likely sentence in this training corpus, right? So this tells us that in the weights of the neural network, in the weights of the language model, there is a lot of knowledge, and in particular, you could argue there's knowledge of what cheese is, or there's certainly knowledge that cheese is connected to these things. And okay, so that's knowledge that the language model has in its weights. And we always knew that language models would have that sort of knowledge in their weights, right? Because, I mean, that's kind of why we trained them. And indeed, this is kind of a fact about the distributional hypothesis, right? The fact that if you just learn to predict what's coming up, over time, your internal representations start to acquire meaning. So this fact was known, you know, for 30, 40, actually, a version of this fact goes back to like the late 50s or something. There's a really interesting old paper on this. But this fact was really new, right? This is something OpenAI kind of discovered recently, that language models are few-shot learners. So here I'm gonna, for the same language model, if I first warm it up with these examples, which basically give the information that what I'm trying to do here is to translate from English to French, then I give it the word cheese, it doesn't do this, it follows the task, right? So this shows us that language models can be flexible in a way that the meta-learning networks I described are flexible and fast learning. The important thing here is that the same model is both flexible and fast at learning, and also slow at holding knowledge. So this is like weight-based knowledge and activation-based knowledge in the same network. And that's super impressive. So we wanted to understand, how can a network do that? Because if we go back to the previous paradigm, when when people were training, here it is, when people were training meta learning or just general weight-based learning, we knew the network could do both of these things, but no network was doing both of them simultaneously. And what's also interesting about the language models is nobody explicitly trained them to be able to do this, right? All they trained them to do is just opt to maximize this probability, the probability of all of the next words in the corpus given all of the segments prior to that, right? So this is the training objective of the language model. So why is it that they emerge with this ability to do flexible few-shot learning and also retain weight-based semantic knowledge? So our hypothesis was maybe it's something to do with the nature of the data that they're trained on. And in particular, if you do this sort of naive predictive learning, which the language models do, but if you do it on data which has this distribution, then maybe, or these distributional properties, then maybe that's what allows it to have this kind of, this ability to do flexible few-shot learning as well as weight-based learning. So language has a very sort of characteristic and well-known frequency distribution, which is of this form. So a zip distribution is kind of a power law, inverse power law distribution. And so it leads to a situation where, you know, there's a small number of words that are like prepositions, which we see all the time, all over language. And then there's loads and loads of rare words that we see very infrequently. And another thing about language is the conditional probability of seeing anything, given that you've just seen it, is much higher than the prior probability of seeing it. So if you do see a rare thing, there's a good chance you might see it again quite soon, even though if you haven't just seen one, its probability of occurring is very, very low. And actually, I'm going to actually argue, well, I think there's good reason for believing that the real world is like this in many ways. It's not just language, right? Social networks, our physical experience of objects, all of these things. In fact, when you put head cameras on children and like code that data for what objects they're looking at, or people they're seeing, their experience is literally of this form. So not just language learners, but language is very characteristic of what language models are trained on. So that's why we looked at that. Okay, so we wanted to study the effect of the distribution on the outcomes in the learner, but in a very controlled way. So we didn't actually use language. We actually went back and used the omniglot challenge, which was the context for original experiments in meta-learning. But we're going to fiddle a lot with the training data, and we're not going to do meta learning. So what we're not going to do is shuffle the labels for any symbols. The labels in all these experiments, the correct label for any of the categories that we show the network is always the same across all the experiments. There's no shuffling. So that's a kind of slightly unrealistic training setting that we're not going to use. And our model is just going to be very much like a language model. So it's just one of these transformers with a small network to embed the images. So what that means is that there is this kind of, I'm just predicting the next word training objective in this system. It's just that we always finish off in each training sample, we finish off with an image, and then it has to just predict the next word, right? And given so that's the context, that's the query, and we're just maximizing the likelihood that the agent predicts the correct number for each category. Given that that's the training setup, there's actually two types of training experience the agent this model might experience, right? So one of them is a situation of might call burstiness. So in one case, the right answer exists in the immediate context. So I think you could probably look at that and tell me that the agent should predict 16 there, right? But in the other case, the burstiness can't come to the rescue. So in this case, how will I know what to predict? Well, I'll know what to predict because it's in my weights, because I've seen one of these things a long time ago in some other sample. Maybe I saw it up there. So in this case, I'm kind of being trained to use my weights. And in this case, I could use my weights, or I could use the immediate context, right? So the question is, in what context is the network going to wind up doing one thing, and in what situations is the network going to be doing the other? And how will we know which strategy the network employs? Well, we just test it behaviorally. So these are testing samples. The agent's not going to learn from these. But if the model can be above chance at the bottom type, we know it must be using its weights. And if the model can be above chance at the top type, we know it must be using activations. And actually, we held out some visual categories. So not only must it be using activations, but we also see that it's able to generalize to novel categories. So it's really learned the strategy of looking back at the context, matching it to what it's currently looking at, and predicting the label for that. Cool. So what we find, so this allows us to kind of take the temperature. Is it doing one type of learning? Is it doing the other? And what we find is that these two things are kind of in conflict. So as we adapt the training data, we see that it tends to learn in weights, or it tends to learn in activations. So if we give it lots more bursty samples, lots of cases where it can solve them using activations or weights, it moves towards using activations, which is quite cool. So you can see here, this is the probability of whether or not in the training set you're getting those bursty samples. And then in this case, on the right-hand side, we find that the cases where we ramp up the bursty samples, its ability to do the in-weights evaluation just totally disappears. So these two things do seem to be in conflict. The network has two possible ways to solve tasks, and it either goes for one or the other. What else makes a difference to which of these two strategies it uses? Well, the total number of categories across the training set, so the number of possible labels that it could ever be required to predict, if we increase that number, then it starts to favor in-context learning. So why might that be? Well, learning in its weights becomes more and more kind of hard in some sense, right? Because you've got more stuff to actually remember. This is kind of like memorization in some sense. This is like flexibly looking at the context. And given that there's more things to possibly memorize, maybe the other strategy kind of becomes more optimal in some way, and that's the one the network goes for. So as you increase the number of categories, the network goes from really fancying memorization and baking things into weights into really enjoying flexibly looking for the context and finding the answer there. Okay, so then what does this relate to language and Zipf's law? Well, we finally tried the situation where the likelihood of each category across the data set was determined in the training data by this Zipfian distribution. So this is much more like the situation we have in language. And what we found was by doing that, that was the only way we could get a network which didn't trade off learning flexibly in weights and learning in activations. It could actually do both, right? So this was the only situation where we got a good score on both types of evaluation. And that situation in particular required a particular zip exponent. So this tells you how skewed this distribution is. And around about the exponent of 1, which is approximately what the exponent that you get in natural languages, you get in a network which is able to do both of these things. One thing none of the networks can do is in-weights learning of the rare classes. So this is a problem for supervised learning, actually. It tells you that if you give networks something very infrequently, it will not learn that in its weights. But actually, this also points to the fact of why might we learn to do flexible learning? Like, why might animals be flexible learners? Well, one reason is because we need to be good at rare things, and gradient descent is not good at rare things. So it needs to be maybe more in context in activation learning algorithm that we're applying. Another fact, this whole experiment, everything I've talked about doesn't work unless you use a transformer. I'm not saying that like RNNs can't do in-context learning. I think they probably can, but image-based in-context learning is very hard in anything other than a transformer. And if you think about what the network has to do, it has to look at the current sample, compare it directly to something in the past, see if they match, and then predict a label as a consequence of that. And it's that direct comparison of a relatively high bandwidth input, an image, which is much easier in a transformer because that information is not compressed through like some, this kind of vanishing gradient problem. It's not compressed through some transition matrix. Instead, in a transformer, with skip connections and stuff, you can kind of pass these representations together and just match them directly. So the emergence of few-shot learning in language models may also be not just a consequence of the training data, but also a consequence of the fact that people started modeling language with transformers and not with recurrent networks. Transformers are better transformers give equal weight to all of the memories that the network has, right? Whereas a recurrent network really fancies the near ones. And you'd think that would be a good bias, like prioritizing near things. But in actual fact, I think it's better to allow the network to develop its own bias towards near things, which is what a transformer can easily do, because that's really a clear bias in the training data. But at the same time, we're not encouraging it to ignore the things in the distant past. So it's kind of like almost it's hard for the network to unlearn the bias that an RNN puts in. If we don't give it that bias, it's better at the rare things, and that's why we get this flexible in-context learning. So anyway, what's this got to do with reinforcement learning? Well, as I said before, it's not just language that's like this or text, it's also the world in general. But when you think about classic reinforcement learning benchmarks, they're not really like this. Often they're sort of artificially uniform. And in fact, all of the ones I've been using for all my other experiments are artificially uniform. And maybe that's why we get such good compositional generalization. Like there's all sorts of things where the uniformness of our RL environments is probably unrealistic. So we created versions of these environments that we often use for our experiments and gave them a kind of Zipfian skew. And yeah, what we found is that most common reinforcement learning algorithms are not good at learning when we give it like very skewed experience. And in particular, much like supervised learning, they're not good at the rare things. So, but what's really worrying is because our evaluations have the same skew, are very skewed, you might not even notice it. So if you average performance across all of the samples in the agent's experience, you might think that the agent's perfect, but actually if you focus in on your evaluations on just the rare things, you'll see that this is actually the graph of the same agent, just measured over different parts of the training distribution. And you'll see that you can often be hiding bad performance on rare things. So if you want to study that problem, you should use our benchmark. And that's it. So I told you, hopefully, in each of these 4 cases, why language and being generally smart can interact, and how language might be a vehicle for learning and training machine learning systems to be more generally intelligent. So when I think about this proposition that maybe to build a perfect language understanding machine, we need to build a generally intelligent agent, I think there's lots of evidence that that might be the case, but I also think it goes both ways, right? So it's also the case that maybe if our goal is to build a generally intelligent agent, we might want to start thinking about how we can use insights from building language understanding machines to make that process easier. Cool. So these are my amazing collaborators who have done a lot of the work that I talked about today. And sorry, gone over time a bit, but hopefully there's time for some questions. So that's it. Thanks.
We actually have one from the online audience. Richie Jatlon is asking, if we use something like decision transformer, do they perform better in the Zipfian environments?
Yeah, that's a great question. What we did try was online learning with an agent that had a transformer memory. And it didn't lead to much better performance in the Zipfian environments. A decision transformer is a specific algorithm for offline reinforcement learning. So in order to test that hypothesis, we probably need some demonstration data, like some expert trajectories, and then we could sort of skew them and see how the decision transformer holds up on the skewed data. So the answer is I don't know, because I haven't got, this is all online RL, and actually one thing we perhaps should do is get some data on these environments with the same skew as the environment naturally has, and then study the problem of offline RL as well. That would be a really nice extension to the benchmark. Also because offline RL is often easier, right? If you don't have a lot of distributed compute and things, offline RL is a bit more like supervised learning, so it's easier for other people to work on. So yeah, that would be a great idea, but I don't know the answer. Yeah, it's an interesting question.
Alice?
Thanks for the great talk. So at some point, I thought you were advocating for language being a good way of abstracting things. I wonder why this would be the case, because there could be some kind of an abstraction that is rather latent, not as explicit as language, that I might capture and represent things. And maybe, you know, as a latent factor, it is for us or for the systems to discover. So I think you got the question.
Yeah. So I'm not saying it's the only useful means of learning to abstract things. It's just, it tends to be quite an effective one. And I think it's an effective one, especially if you want to train networks to do things that humans are good at. Probably because in human evolution, that was also an optimization. And so the abstractions, whether they were sort of non-linguistic initially or not, they then became the ones that we talk about. And so those two things are very confounded, right? The existence of language might point to the right abstractions in a non-linguistic environment. And so because we want to talk about them, we have words for them. Or it could be also the case that the things that we got used to talking about then also became the abstractions we tended more to use. And there's actually lots of evidence that the causation goes that way as well, at least in humans. So I don't know what causes what, but I think that's sort of intuitively a reason why good abstractions and language might be the same thing in many cases. Yeah, that's kind of my intuition. So yeah, I guess it's because and why would that system optimize in that way? Well, because being good at both abstraction and language helps us ultimately do things, right? So being good at language helps us coordinate with other humans, so we can do things like, I don't know, build the pyramids or go to the moon. And being good at abstraction helps us think our way through the physical world. And so for both of those things, we get more reward in our evolution reward function. So that's kind of how it emerged. That would be my really pop evolution explanation. But yeah, I stand to be corrected by people who actually know what they're talking about on that question.
We're going online in person one each. So now Guy Lupian, hope pronounced well. said, hey, Felix, question about the odd one out task with explanations. Where does the knowledge of what large means come from, such that the agent can benefit from getting it in an explanation?
Yeah, so I think the word there should be larger or smaller, because I think, okay, so there's some absolute, those, yeah, I mean, large is obviously a very relevant, relative term. So, and it's also like, even with people, it depends on the thing that we're using to modify, you know, so like a large elephant is very different from a large spider, etc. So in these experiments, the meaning would be better described as largest or larger and smaller or smallest. But there's two objects in each set of four. If size is a factor, then there's two objects that are potentially, or there's some number of objects which are big and some number of objects which are small, and they're approximately the same size, even though their shape is different. So that's kind of where the agent can do it all relatively. It can work it all out relatively. So it doesn't need any sort of a priori knowledge. It can just pick this up over the course of many, many episodes. So it's rather a difference in size. But these words refer to a difference in size, rather than that curious mix between absolute and relative, which is what they tend to mean in people. Yeah, that would be that's basically a good question.
Of reinforcement learning, we talk about a lot about rewards. So being rewarded. A lot of people argue that what makes us special as human is pain and suffering. The fact that we feel the pain and the suffering because we are biologicals, we can even have a lethal outcome if we don't do something properly. A machine, by definition, doesn't feel the pain and suffering. How do you think that you could introduce that kind of non-reward, the total opposite of a reward?
So I think reinforcement learning would be my answer if I hadn't already talked about reinforcement learning. So it's intended to model, I mean, reinforcement learning is kind of an attempt to model that, maybe at the expense of a lot of the other kind of things that humans like. So, I mean, I'm not going to argue, it's very philosophical whether or not an agent that's very...
You can do game over and start again.
That's true. Yeah, so it probably doesn't ever, it's probably never going to experience that sense of doom. That's in some sense that humans would.
It's so important for humans to learn.
Yeah. But certainly when you train, especially maybe one answer is we should have more non-resetting environments, right? We should have more lifelong experiences so that you can understand like the implications of repeated negative experiences of things. Yeah, so that could be one answer, but certainly it's true that when you train agents using reinforcement learning, they do exhibit some of the same behaviors that humans exhibit in the face of pain or suffering. They can exhibit very sort of like classic repulsive behavior in the face of things which they know give negative, like almost realizing what something is and then coming. But now that's all me really imposing my interpretation on the behavior of an agent, which the agent could be just moving in certain ways. So clearly there's a lot of, I'm sort of overstretching it by claiming that these two are the same things. But I would say reinforcement learning is a good mechanism for capturing those drivers of human learning in a way. It's the ones that are more higher order or more abstract that it's not so good at capturing, I would say. The ones like, I don't know, like, you know, I just feel like being better at stuff because it's good for my career, or I don't know. Those are the ones that I'm not sure. I don't know whether, yeah. So anyway, yeah, I don't have a better answer than reinforcement learning, but I agree. That is a really interesting question, and I do think also that there's an argument for sort of more evolutionary methods combined with reinforcement learning, because that's one way in which I think you can learn from death, right? Like we've needed, I think, a lot of that sort of knowledge of how bad things could potentially be that could actually be transferred in genes. So it's the human population that had to learn that, because nobody in their lifetime could ever really learn about those things almost by definition. So, yeah. Yeah. Yeah.
Okay. Soon you, online ask, do you see there is a chance to integrate these separate capability aspects? Is the bottleneck benchmark or methodology?
I think that probably refers to a particular point in the talk,
yeah.
So I can't.
He just sent it after the other ones, so I'm not sure it will be something soon enough.
Yeah, I might have to pass on that one just because I don't know exactly what it's referring to.
So, okay, let's go in order. You.
You kind of touched on it. Was it me? Sorry.
No, it was behind you.
Sorry.
I'm happy to stay for like until the questions run out, but I know that, so I'm totally happy with that. But I don't know if anyone.
What you've done was what your intuition would be on maybe not using language as a board, but I think just play a game together where they need to learn the language more to solve it.
Yeah. So I think this also relates. There's a number of things going on there. So one is that in the experiments I've described here, they're not very. I don't see a lot of potential in these paradigms for learning about the kind of social knowledge, right? Like, what would it take to learn about another agent and the fact that that other agent has goals and desires, and how can we align? And all of everything I've described here, there's kind of a God which is giving the agent some language, and then a world and maybe some reward, but there's not the ability to learn about other people. So I think the sort of pragmatic aspects of language as a communicative tool are not well covered here. And maybe it would require two agents, which initially learn language in some slightly passive way and then learn to communicate, that would help these situations endow the agent with like more social knowledge. That's one thing worth saying. Another thing is reinforcement learning in this sort of simulated way where I create an environment and then I train an agent. That's also very limited with respect to language in some ways, because for a lot of the things that I might ask an agent to do or want an agent to do, it's almost as hard to recognize that they've been done correctly as it is to maybe learn how to do them, right? And so if I could have a program to check whether something had been whether an instruction had been executed perfectly, if I had such a program, I could probably use similar knowledge to actually just program the agent to do it anyway, right? So I'm thinking of things like, what if the task is like, I want an agent which learns to tidy a room. So what do I have to program into the environment to reward the agent? Like, what does tidiness look like? What's the code for tidiness? Or what's the code for beauty? Or what's the code for like moving around in a circle? Well, actually moving around in a circle, you could potentially approximate with some with some knowledge of mathematics. But the point is that in the general case, we can't use code to write a simulator to check whether things have been done correctly. Or at least that's at least as futile as, for example, writing code to look at the pixels in an image and tell you what's in the image, right? It's like, we know that can't be done very easily in the general case. And so we need learning-based methods. And I think so, but I kind of see the future of RL as being a bit more like the way animals use reinforcement learning, which is things happen in the world. Part of the learning system translates that into a signal that might reward, and a different part of that learning system learns from that. So that first bit would be something like a language conditional or multimodal reward model. And so I think all good agents should have one of those, so that there doesn't need to be rewards in the environment. Yeah.
Okay, I think we should stop here for the questions. We're gonna have some food now and some time, but the talk was meant to last 1 hour. So before you leave or you start eating or asking more questions, the next, I forgot to mention before, these talks are sponsored by DeepMind. So those are the ones you have to thank for the food that we're going to have now. And also next month, we're having on the 16th of November, a talk from Tim Roxtel, I hope I have pronounced well, about open-ended reinforcement learning and continual learning. So it links with some of the questions we have here. And also on the 30th of November, we're going to have Al-Hussein Fawzi, who is the lead author of the Alpha Tensor paper about more rapid matrix multiplication, also coming as well. So hope to see you there. It's not the end, you can stay, but for those of you who only came for the talk, you can leave now. Thank you for coming.